Hello and welcome to Lie algebras. In this lecture, lecture number 11, we will talk about root space decomposition for complex semi-simple Lie algebras. Let's start with our setup. For this lecture, G denotes a semi-simple finite-dimensional complex Lie algebra, and H denotes a fixed Cartan subalgebra of G. Recall from the previous lectures that any element in this Cartan subalgebra acts semi-simply, that is diagonalizably, on the Lie algebra. Also recall that the Cartan subalgebra of a semi-simple finite-dimensional complex Lie algebra is abelian, so the bracket of any two elements in H is 0. This allows us to introduce the following notation. For any linear functional alpha on H, we denote by G sub alpha the set of all elements G in G, which have the following property. The bracket of H with G is equal to alpha of H times G for any element H in H. In other words, G sub alpha is the set of common eigenvectors for the elements in the Cartan subalgebra with the eigenvalues prescribed by the linear functional alpha. Directly from the definition and the property that each element in H acts diagonalizably on G, it follows that the Lie algebra G decomposes as a direct sum of these subspaces G sub alpha over all alpha in the dual space to the Cartan. Also, we recall that G sub 0 coincides with the Cartan subalgebra H because any Cartan subalgebra is self-normalizing. We will say that a linear functional alpha on H is a root of our Lie algebra G, provided that alpha is a non-zero linear functional and the corresponding space G sub alpha is not zero. We will denote the set of all roots of G by phi. Since our algebra G is fixed, in general one can use phi sub G. And this set phi is usually called the root system of G. So the root space decomposition of the Lie algebra G is given in the following way. So the Lie algebra G is isomorphic to the direct sum of the Cartan subalgebra H plus the direct sum over all roots alpha of the Lie algebra G of the corresponding subspaces G sub alpha. Since G is finite dimensional, it is clear that phi is a finite set. We will need the following very useful tool, which is called Clinica Schrock theorem. It's a relatively analytic statement, which was proved by Clinica and Schrock in 1950s, and the theorem itself is as follows. Assume that we have two elements x and y, which are bounded linear operators on some Banach space. Assume further that x commutes with the commutator of x and y. Then the commutator of x and y is quasi-nilpotent, which means that the spectral radius of this operator is 0. The original proof of this statement is very short and elegant, but is of analytic nature, so we refer to the original paper, for example, of Clinica on operator commutators in the Proceedings of the American Mathematical Society, which can be found online for the full proof. In our particular case of finite-dimensional vector spaces, this theorem has the following application. If we have two linear operators x and y on a finite-dimensional complex vector space, such that x commutes with the commutator of x and y, then the commutator of x and y is nilpotent. The claim of Clinica Schrock theorem is that its spectral radius is 0, but then for finite-dimensional vector spaces this means that the commutator of x and y is nilpotent. So now we are going to associate to each root of our Lie algebra a certain SL2 subalgebra of this Lie algebra. So we fix a root alpha and a non-zero element A in the corresponding root subspace G sub alpha. Claim. First of all, minus alpha is also a root of G, and there is an element B in the root subspace G sub minus alpha, such that the linear span of A, B, and their commutator is a subalgebra of G isomorphic to SL2. Proof. First of all, we recall that we have the Killing form K on our Lie algebra, that it is non-degenerate, and that the root subspaces G sub beta and G sub gamma are orthogonal with respect to this Killing form unless the sum of beta and gamma is 0. Therefore, the only subspace where we can have an element whose Killing form with alpha is non-zero is a subspace G sub minus alpha. So there must exist an element B in G sub minus alpha such that the Killing form of A and B is non-zero. In particular, minus alpha must be a root. So now we pick an arbitrary element U in our Cartan subalgebra H, which has the property that alpha of U is non-zero. This is of course possible since alpha is a root, so alpha is a non-zero element in the dual space. Let us evaluate the Killing form at the element U and the commutator of A and B. First of all, using the associativity of the Killing form, we can write it as a Killing form of the commutator of U and A and B. The commutator of U and A is equal to alpha of U times A because U is an element of the Cartan subalgebra and A is an element of G sub alpha. Now alpha of U is a scalar, we can move it out and get the expression alpha of U times K of A comma B. Alpha of U is non-zero because of our choice of U, and K of AB is non-zero because of our assumptions before. So this means that this expression is non-zero, and in particular, the commutator of A and B must be non-zero. So we deduce that if we have a non-zero element A in G sub alpha, there must exist a non-zero element B in G sub minus alpha, such that the value of the Killing form at the pair AB is non-zero. And in this case, the commutator of A and B is non-zero as well. So next we claim that the value of our functional alpha at the commutator of A and B is non-zero. Assume that this is not the case and that alpha of AB is 0. Then, by definition, the commutator of this commutator of A and B and A is 0 because it is equal the evaluation of alpha at the commutator of AB. The commutator of AB is an element of the Cartan subalgebra times A. So if alpha of the commutator of AB is 0, this is 0. Then we can use the Clinica Schrock theorem and deduce that the commutator of A and B is an nilpotent element. So the adjoint operator associated to the commutator of A and B must be nilpotent. But at the same time, this commutator belongs to the Cartan subalgebra, so it must be a semi-simple element because the adjoint operator of any element of the Cartan subalgebra acts diagonalizably on the Lie algebra. So when we have an element which is at the same time nilpotent and semi-simple, this element is 0, and this contradicts our previous observation. Therefore, we can define a vector space A, a subspace of our Lie algebra G, which is spanned as a vector space by the elements A, B, and the commutator of A and B. We observe that if we commute A with the commutator of A and B, since the commutator of A and B belongs to H, we will get A times the scalar, which is computed using the evaluation of the commutator of A and B via the linear functional alpha. Similarly, the commutator of B with the commutator of A and B belongs to A. This implies that A is actually a Lie subalgebra of G. So all non-trivial brackets stay in A. And then it is very easy to check that the following map defines an isomorphism between SL2 and this Lie algebra A. So we just sent the element E of the standard basis of SL2 to A, the element H of the standard basis of SL2 to the commutator of A and B times the scalar 2 divided by the value of alpha at this commutator. Note that we know that this value is non-zero, so this expression is well defined. And finally, we sent F to the scalar multiple of B with the same scalar, 2 divided by alpha of the commutator of A and B. It is straightforward to check that the linear bracket of these elements has the same structure constants as the Lie bracket in the Lie algebra SL2. So this proves our claim that we have an SL2 subalgebra A of G associated with our choice of a root alpha and a non-zero element A in the corresponding root space. Okay, so we keep the choice. We have our root alpha and we have the corresponding SL2 subalgebra A associated to a choice of a non-zero element in G sub alpha. alpha. Next, we consider the subspace V of G given by the direct sum of all root subspaces corresponding to those roots which are scalar multiples of alpha. Of course, V is finite dimensional because it's a subspace of a finite dimensional vector space. Moreover, since the bracket of G sub alpha and G sub beta is a subset of G sub alpha plus beta, this we saw in the previous lectures, it follows that our vector space V is actually an A module, and since it's finite dimensional, it's a finite dimensional A module. For the standard basis of SL2, the roots of SL2 are 2 and minus 2, and for this choice of roots, we know from the theory of finite dimensional SL2 modules that any finite dimensional SL2 module has weights which are integers. So they belong to the 1/2 of the lattice spanned by roots. From this we deduce that any root beta in phi, which is a scalar multiple of alpha, must be a scalar multiple of alpha where the scalar is given by a half integer. Of course, we are free to choose any alpha we wish. So if we choose alpha to be the longest, so given by the maximal possible scalar, then we get that the only possibilities for such roots in phi are plus minus alpha and plus minus 1/2 of alpha. So there can be at most 4 roots which are scalar multiples of alpha. Next, we note that the kernel of alpha, this is a subspace of the Cartan subalgebra, is actually a module over our SL2 subalgebra A. This is because if we take any element H in the Cartan subalgebra and bracket it with our element A of the algebra A, we get a scalar multiple of A with a scalar given by minus of alpha of H. So if H belongs to the kernel of alpha, we will get 0. Similarly, the bracket of B with this H is also 0. So all elements in the kernel of alpha are killed by both A and B, so they form a submodule which is just a direct sum of trivial A modules. And the number of summons is, of course, the dimension of this module. So let's consider 2 cases. So we again assume that alpha is the longest root. So case 1, that 1/2 of the alpha is not a root. This means that the only roots which are scalar multiples of alpha are plus and minus alpha. In this case, we deduce that our module V must be the direct sum of the adjoint representation of A with the kernel of alpha. This is because under this assumption, all weights of the module V are integer multiples of alpha. And each simple module whose weights are integer multiples of alpha must have a 0 weight space. At the same time, in the 0 weight space, which is Cartan, we have the kernel of alpha, which is a codimension 1 subspace, which is an A module. So this means that there can only be at most 1 more A module, which is a direct summand of V. And we of course know that the algebra A itself is a submodule of V under the adjoint action. So this is the first case. And the second case, if the half of the alpha is a root. In this case, we can change the root alpha to this half of the alpha. Let's denote this new root by alpha prime and consider this corresponding SL2 subalgebra A prime. Then by the same argument as we just had, V should be the direct sum of A prime, the kernel of alpha, and one more additional submodule W, which should contain as a non-zero weight space the root subspace G sub alpha. But then this submodule must also have a weight subspace of weight 0. But this is a contradiction because the 0-dimensional weight space coincides with the Cartan and it is completely covered by the previous 2 summons. So this leads to contradiction, and this means that case 2 cannot occur. Consequence, we only can have case 1, which means that alpha and minus alpha are the only roots which are scalar multiples of alpha, and because of the fact that V is a direct sum of A and the kernel of alpha, the dimension of the root subspaces G sub plus minus alpha is 1. Now we want to identify H and its dual space using the Killing form, whose restriction to H is non-degenerate. So for each root alpha, we define the element C sub alpha in our Cartan subalgebra via the identity that the value of the Killing form at C sub alpha and any element h in H is equal to alpha of H. So this uniquely defines C sub alpha because the Killing form is a non-degenerate form. We can uniquely define the element C sub alpha when we prescribe the value of the Killing form evaluated at it and any element h in H. So we claim that the commutator of the one-dimensional root subspaces G sub alpha and G sub minus alpha belongs to the subspace generated by this element C sub alpha. So this is a subspace of the Cartan subalgebra. To prove it, take any element x in G sub alpha, any element y in G sub minus alpha, and any element h in the Cartan subalgebra. Let us compute the value of the Killing form at the pair h and the commutator of x and y. Using the associativity of the Killing form, we write it as the value of the Killing form at the commutator of h and x and the element y. The commutator of h and x is equal to alpha of h times x. This is because h is an element of the Cartan subalgebra and x is an element of G sub alpha. Now we can move out the scalar alpha of h, and now we can use the definition of the element C sub alpha to write alpha of h as the value of the Killing form at C sub alpha times h. Now we can use that the value of the Killing form at the pair x and y is just a scalar, which we can now move into the evaluation of the Killing form at the pair C sub alpha and h. So we get the value of the Killing form at the element C sub alpha times k of xy and the element h. And we use that the Killing form is symmetric and swap the arguments. Altogether, we get that k evaluated at h and the commutator of x and y is equal to k evaluated at h and the element C sub alpha times k of x and y. Since k is non-degenerate, and this is true for any element h in H, we deduce that the commutator of x and y equals C sub alpha times the scalar k of x, y. And this is, of course, an element in the subspace generated by the element C sub alpha in our Cartan subalgebra H. We can summarize the above in the following way. For any root alpha in phi, the root subspaces G sub alpha and G sub minus alpha are one-dimensional, and when we take their direct sum, together with a subspace generated by the element C sub alpha in the Cartan subalgebra which we defined, this direct sum forms a Lie subalgebra of G, which is isomorphic to SL2. We denote this Lie subalgebra SL2 sub alpha. Clearly, it depends only on the root alpha. And for each alpha, we can pick a basis of this SL2 subalgebra, the element E sub alpha in G sub alpha, F sub alpha in G sub E minus alpha, and the element H alpha, which is a bracket of E sub alpha and F sub alpha, which form a standard basis of the corresponding SL2 subalgebra SL2 upper alpha. Under these assumptions, the value of alpha at the Cartan element H sub alpha will be equal to 2, because this is true for our standard basis in SL2. The adjoint action of H on E gives us 2E. So 2 is the root of SL2 for the standard basis. So let us deduce now some further properties of roots. Assume that we have two roots alpha and beta, and such that beta is not a scalar multiple of alpha. We claim that the value of beta at the element H sub alpha from our SL2 subalgebra SL2 upper alpha is always an integer. We claim that the difference of beta with a scalar multiple of alpha given by this scalar, the value of beta at H sub alpha, is also a root. And we claim that in the case when alpha plus beta is a root, then the commutator of G sub alpha and G sub beta equals the commutator of G sub alpha plus beta. From previous lectures, we know that there is an inclusion. The commutator of G sub alpha and G sub beta is a subset in G sub alpha plus beta. We claim that this is an equality. Proof. So we consider the subspace of G given by the direct sum of all root subspaces G sub B plus K alpha, where K is an integer. Of course, it's a finite dimensional module over our SL2 subalgebra SL2 upper alpha. Note that the value of B at H sub alpha is an eigenvalue of H sub alpha on this module. So it must be an integer because of our theory of finite dimensional SL2 modules. Also, we know that if we have a finite dimensional SL2 module which has a weight k, then minus k is also a weight of this module. So since we know that beta of h sub alpha is an eigenvalue of h sub alpha on V, then minus beta of h sub alpha must be an eigenvalue of h sub alpha on V. And taking into account that the evaluation of alpha at h sub alpha is equal to 2, we can write minus beta evaluated of h sub alpha as beta of h sub alpha minus beta of h sub alpha times alpha of h sub alpha. This implies that beta minus beta of h sub alpha times alpha also must be a root of G. We can also deduce that V is a simple SL2 module since all weight spaces of this module are one-dimensional. This is because beta is not a scalar multiple of alpha. The subspace G sub 0 is not a subspace of V, so our Cartan subalgebra is not a part of V, and all other root subspaces of V are one-dimensional. And if you have a simple finite dimensional SL2 module, if alpha plus beta is a root of phi, this means that our weight subspace for the root beta is not the highest weight of V. But this means that the action of the element E sub alpha of our SL2 algebra on this weight space is non-zero. So the commutator of G sub alpha and G sub beta is not a zero space. Since all involved spaces are one-dimensional, it follows that this commutator coincides with the weight space G sub alpha plus beta. Finally, we establish also the generating property for our roots. Claim the set phi spans the dual of the Cartan subalgebra as a vector space. Proof assumes that this is not the case. We can then take the intersection of the kernels of all roots, and this is a subspace of the Cartan subalgebra, and if phi doesn't span the dual of H, this intersection must be non-zero. So we can take a non-zero element H in this intersection. Then this element H commutes with all elements in all root subspaces simply because the commutator is given by the evaluation of the root at H, and since H belongs to the intersection of all kernels, this evaluation will be zero. So our H commutes with all root subspaces, and of course it commutes with the Cartan subalgebra because later is abelian. So our H is an element of the center of our Lie algebra. But the center of our Lie algebra is trivial because our Lie algebra is semi-simple, so this leads us to a contradiction. Therefore, the element H must be zero, which means that the intersection of all kernels must be zero, which means that phi spans our dual to the Cartan subalgebra. Now we can summarize all properties of our set phi of all roots. First of all, we have finitely many roots. The zero functional is not a root, and we know that the set of all roots spans the dual space to the Cartan subalgebra. Moreover, if we have a root alpha, then the only roots which are scalar multiples of alpha are plus and minus alpha. If we have two roots alpha and beta, then the evaluation of beta at the element H sub alpha, so this is a Cartan element of the SL2 subalgebra corresponding to alpha, is always an integer. And if we have any pair of roots alpha and beta, then beta minus the scalar multiple of alpha given by evaluating beta at the element H sub alpha is again the root. So we will use this list of properties in the next lecture, which will be devoted to classification of all root systems. Thank you very much. Hope you enjoyed the lecture.